looking at the equations for the induction machine. We saw the model of the induction machine in the natural reference frame, and then we have derived an approach to transform the natural reference frame model into the alpha beta reference frame, which we said is essentially a two-phase description. So, what we have done is gone from 3-phase to two-phase description. We have seen the form of equations in the 3-phase case, and we have seen the form of the equations in the 2-phase. Needless to say, the two-phase description also includes the zero sequence component, including zero sequence, which, as we said, for the most part is not there in a 3-phase machine if the system is operating in the normal way. So, let us look at, we have seen how the equations look like. Let us look at the input variables themselves. In the 3-phase case, you have 3 inputs, which is VA. Let us say that VA is Vm cos omega t, then VB would be Vm cos of omega t minus 2 pi by 3, and Vc would be Vm cos omega t minus 4 pi by 3. And while going from 3-phase to 2-phase, what we are doing is transforming all the variables from the 3-phase to the 2-phase reference frame, and therefore what we have is V alpha, V beta and V 0. This is equal to square root of 2 by 3 is there, and then 1 minus half and then minus half, 0 root 3 by 2 and minus root 3 by 2, 1 over root 2, 1 over root 2 and 1 over root 2. So, if you want to get V alpha, V beta and V 0, you need to substitute the expressions for VA, VB and VC in this vector. So, that is what you have here, VA, VB, VC. Note that we are substituting the actual values as a function of the variable t, and therefore, what we are substituting here is not the RMS value or a phasor in this place, it is the actual function of t, and therefore, what we end up with is V alpha is root of 2 by 3 multiplied by Vm cos omega t minus half of Vm cos omega t minus 2 pi by 3 minus half of Vm cos omega t minus 4 pi by 3, and therefore, this is nothing but, or we can say Va minus Vb by 2 minus Vc by 2, which is root of 2 by 3 into Va minus of Vb plus Vc by 2, and Vb plus Vc is nothing but minus Va, because Va plus Vb plus Vc is equal to 0. Obviously, it is a balanced excitation that we are giving. So, in that case, then what you have is root of 2 by 3 multiplied by 3 by 2 into Va. So, this is root of 3 by 2 into Vm cos omega t. So, V alpha turns out to be square root of 3 by 2 into Vm cos omega t. What happens to V beta? So, V beta is nothing but root of 2 by 3 multiplied by Vm cos omega t minus 2 pi by 3 minus Vm cos omega t minus 4 pi by 3 multiplied by root of root 3 by 2. So, that is the expression. So, that is nothing but root of 2 by 3 into root of 3 by 2 multiplied by Vm multiplied by cos of omega t minus 2 pi by 3 minus cos omega t minus 4 pi by 3 and so this expression can be written as cos omega t cos 2 pi by 3 plus sin omega t sin 2 pi by 3 and then you have minus cos omega t cos 4 pi by 3 minus sin omega t sin 4 pi by 3, that is what is there enclosed in the square brackets. Cos 2 pi by 3 is cos of 120 degrees, that is minus half. Cos 120 is cos 90 plus 30, that is minus sin 30, that is minus half, and then sin 2 pi by 3 is root of 3 by 2, that is sin 120 is sin 90 plus 30, that is cos 30, that is root 3 by 2, and then cos 4 pi by 3, cos of 4 pi by 3 is cos of 240 degrees, that is cos of 180 plus 60 degrees, that is minus cos 60 degrees. So, that is plus half, and then this is again so plus root 3 by 2, and therefore what you can see is this term and this term cancels. So, what you are left with is root 3 sin omega t multiplied by Vm into root 3 by 2 into root of 2 by 3, that is nothing but root 3 cancels and then you have root 2. So, you have root of 3 by 2 into Vm sin omega t. So, this is nothing but V beta and your V alpha was root of 3 by 2 into Vm cos omega t. So, you see that the variables that are exciting the induction machine in the 2 phase are applied voltages that are phase shifted by 90 degrees, whereas in the 3 phase machine the applied voltages are phase shifted by 120 degrees. So, a 2 phase induction machine whose applied excitations are phase shifted by 90 degrees with respect to time will behave the same way as a case of a 3 phase induction machine whose excitations are phase shifted by 120 degrees with respect to time. The equations of course have appropriately been modified as we saw in the last class, and therefore since these two machines are equivalent, the machine description should also be obtainable by looking at the 2 phase at the beginning itself. Instead of going from 3 phase to 2 phase, we could start writing the expression directly from the 2 phase system. So, how can you do that? And we should also look at another aspect before we go to that. V0 is nothing but root 2 by 3 into 1 over root 2 times Va plus 1 over root 2 times Vb plus 1 over root 2 times Vc, and therefore we already know that this equation holds, Va plus Vb plus Vc is 0. So, it is root 2 by 3 into 1 over root 2 into Va plus Vb plus Vc, and this is already 0. So, when you excite the 3 phase machine with a balanced excitation, the 0 sequence component goes to 0. You have only the alpha term and V alpha term and V beta term. That is why we again call it as 2 phase equation. So, how do we get the machine equation directly from the 2 phase case? Now, let us say that we have a 2 phase machine. In the 2 phase machine, what we have is the alpha axis and the beta axis for the stator. So, it means that you have a winding whose MMF axis is along the alpha axis. The symbolism to denote a winding whose MMF is along a particular axis is in this way. So, this is the alpha S, and then you have the beta winding for the stator which is producing MMF along the beta axis, and similarly the ABC of the rotor have also been transformed into the alpha beta reference frame, but however the alpha beta of the rotor are rotating along with the rotor, and therefore you have an alpha axis of the rotor and a beta axis for the rotor. So, to distinguish them, we will call it as alpha S, alpha R, beta S, and then beta R. And you have a coil here in the sense you have a coil on the rotor which is producing an MMF along the alpha R axis, and then you have a coil on the beta R axis as well. In representing this way, we are not making any reference to the 3 phase machine, we are starting directly from a 2 phase machine, and this angle is the rotor angle theta r, and therefore that angle is also theta r. Now, when we write the equations, we need to know how the flux lines are going to be oriented, and therefore we consider dot points here, and we consider that flow of current is into the dot point here, that is your I alpha for the stator, and this is the rotor variable I alpha. Voltage applied here is V alpha, voltage applied here is V alpha. Similarly, for the beta winding, this is I beta, and I beta is here, V beta and V beta. So, this is a general representation of a 2 phase machine. How does one write equations for this? If you want to write the expression for V alpha, that is applied voltage on the stator alpha phase, you would write R S, resistance of the stator, times I alpha plus P times psi alpha, and psi alpha is the flux linkage of the coil on the alpha axis of the stator, and that is nothing but the self inductance of the stator coil multiplied by I alpha, that is the flux which is caused by its own flow of current. Then of course there will be a mutual linkage between, if you want to consider between beta S and the alpha S, there is no flux linkage between the two, because beta S is at 90 degrees with respect to alpha, and therefore flux linkage is 0. Maybe we can write it as 0 into I beta. And then there would be a flux linkage because these two axes, alpha r axis and the beta r axis, are rotating. So, there will be a mutual flux linkage between this coil and this coil, and if you call that as M MSR times cos theta r multiplied by I alpha, that is the current that is flowing here. In order to distinguish this MSR from whatever we had written earlier as MSR in the 3-phase machine case, we will simply call this as MSR bar, and then you have a flux linkage due to this coil here, and that is MSR again into cos of 90 plus theta r multiplied by I beta. These two values MSR for the alpha axis and the beta axis are the same, because we assume that this winding and this winding are identical in all aspects except that they are displaced with respect to space, and therefore if an I beta flows here and if this coil were really oriented along this axis, the self inductance would have been the same. Therefore, MSR is really the same, and therefore this can be written as Ls into I alpha plus 0 times I beta plus MSR cos theta r into I alpha, and then cos of 90 plus theta r is minus MSR bar sin theta r into I beta, and therefore this is what you are going to substitute here. Now similarly, one can write expressions for V beta as well. I will leave it to you as an exercise to write down the expression for V beta. Now let us write the expression for V alpha r, that is nothing but in our notation V alpha. V alpha is RR RR into I alpha plus P times psi alpha, and where the expression for psi alpha will then be L R into I alpha, that is self inductance multiplied by the flow of current in itself, plus there will be no mutual flux linkage between the coil alpha r and beta r, because they are stationary with respect to each other and separated by 90 degrees, and therefore there will be no mutual linkage due to that. So you have 0 into I beta. There will be flux linkage between these two, and therefore that is nothing but the same MSR multiplied by cos theta r multiplied by I alpha, and then you have mutual between these two terms, that is nothing but MSR multiplied by sin theta r multiplied by I beta. Now you, in order to formulate the equation, you need to substitute the psi alpha here, and if one does that, you get the expression V alpha equals R alpha Rs into I alpha plus Ls P into I alpha plus the differentiation of the last two terms involving MSR will give rise to two terms each, because the derivative of MSR cos theta r I alpha plus or minus MSR sin theta r I beta. In this expression, both I alpha and the rotor angle are functions of and therefore you need to differentiate both of them, Rs I alpha plus Ls P I alpha plus you have MSR cos theta r P of I alpha, you are differentiating this, and then you have plus MSR into minus sin theta r d theta r by dt into I alpha. So, this term is expanded at these two because theta r is a function of time and I alpha is a function of time. And then coming to the second term, you have minus MSR sin theta r P I beta, and then minus MSR cos theta r d theta r by dt into I beta. And if you look at this expression, you will find that this is the same as what, say, this has the same form as what we had derived in the earlier lecture. If you remember, we had V alpha beta 0 equals R times I alpha beta 0 these are vectors, plus we had L alpha beta 0 P of I alpha beta 0. Then we had a matrix which we called as G multiplied by d theta r by dt. G is again in the alpha beta 0 reference frame multiplied by this vector I alpha beta 0. Elements of this G matrix would then come from these terms. These entries would go into the G matrix. You have d theta r by dt and the vector I alpha beta 0 will compose of these things. The inductance matrix on the other hand would comprise of terms like this, derivative of P I would come here, and the resistance matrix is of course going to remain like this. In this manner then one can write the expression for V alpha also, stator for the expression for the rotor, and you would get a similar looking expression which again falls into this format. And therefore, this equation in the alpha beta 0 reference frame can be written directly by observation. The only thing is that we do not know how this term MSR bar is going to be related to what was MSR derived from the 3 phase case, and that we have seen now that MSR bar is nothing but 3 by 2 times what we had written as MSR in the 3 phase machine. Similarly, this inductance Ls, what we find is that Ls is nothing but, we have written the self inductance here which would be a leakage inductance along with some along with the magnetizing inductance, and we found that Ls is nothing but the leakage inductance plus 3 by 2 times the magnetizing inductance. So, if we remember these things, then the expression for the 2 phase machine can be written directly from by looking at the 2 phase axis. We of course will not have an expression for V0. If you remember, V0 for the stator was nothing but Rs plus Ls P multiplied by I0. I alpha and I beta do not figure in this expression. Similarly, V0 for the rotor was Rr plus LLR P into I0 for the rotor, the alpha axis of the rotor and beta axis of the rotor, I alpha and I beta here do not figure in this expression as well. So, if one remembers this also, one can complete the alpha beta 0 description of the machine from the elementary ideas. So, we have now converted this 3-phase machine to a 2-phase machine, and the 2-phase machine will work in the same way as the 3-phase machine, provided you give excitations that are 90 degrees in phase to the alpha and beta axis. But have we simplified anything? Now, in the expression for the 3-phase machine, we found that we had an impedance description. The operation, if you put this expression as V equals some Z into I, this Z was a 6×6 matrix, and this matrix was a function of rotor angle. What we have done is we have reduced this to another description, this V equals Ri plus L into Pi plus G theta r d theta r by dt. This equation can be compressed and written again in this form, which is nothing but R plus L into P plus G into omega multiplied by I. So, which can be written as some Z into I. This could be in the alpha beta 0 reference frame, again alpha beta 0 everywhere. This description, if we exclude the 0 sequence parts, this impedance matrix is only 4×4. So, excluding 0 sequence. But even though we have sort of apparently reduced the size here, the matrix is still dependent on rotor angle. If we want to solve, remember our goal is to get hold of a model for a machine using which we will be able to determine how the machine is going to behave with respect to time for any given inputs that are applied as VA, VB, VC or V alpha, V beta and so on. That means we need to be able to solve this set of equations in order to arrive at the dynamics of the machine. So, how does one solve these equations? These equations are not simple, these equations are not linear, they are non-linear equations because of this term omega into I, and therefore, it is quite difficult to solve by hand. You would need to take recourse to some digital computer algorithms in order to solve these set of equations. However, if you are going to take recourse to a digital computer and this is the equation that you have, let us say, what will you do? You can recast this equation as L Pi equals V minus R into I minus G into omega into I. So, having written it in this form, this looks like a first order differential equation set where you can write Pi as L inverse multiplied by V minus Ri minus G omega I. This is an equation for the electrical subsystem part of it, and then you have the mechanical system, which would say J d omega by dt is the torque developed minus whatever load torques are there on the system. This torque developed will then be a function of I. We have already seen I transpose into Gi is the generated torque, and therefore, one can substitute that expression here. So, these two sets of equations or this entire set of equation is what has to be solved in a digital computer in order to obtain the dynamics for a given input vector V and a load torque TL. But the process is not again very easy, because in the digital computer one would solve it by algorithms known as numerical integration algorithms. And these numerical integration algorithms essentially take the axis of with respect to time. Let us say you want to compute the solution, maybe some current I with respect to time. What they do is, the numerical integration algorithms consider discrete instants of time along the axis and try to estimate the solution at each instant of time. So, maybe at this instant of time solution is here, value of I is here, at this instant it is somewhere else, this instant it is somewhere else, here it is somewhere else. So, we could say that the current sort of flows like that. So, you discretize the axis and then try to compute the solution at each instant of t that you are willing to consider, which would mean that this inductance matrix has to be evaluated, all these have to be evaluated at every instant of time. R matrix is a fixed matrix, you can evaluate it once and store it. G matrix is not a fixed matrix because it is going to depend on angles. Inductance matrix is again not going to be a fixed matrix because it depends on the rotor angle, and the inductance matrix you have to compute either the inverse or do something in order to get the solution, and therefore evaluating the solution is going to be a difficult job, because these G and L are going to change at every instant. At every instant they are going to change, because the rotor angle, as the rotor is going to rotate, the rotor angle obviously is going to change, and therefore L matrix and G matrix are changing with respect to time. This makes the solution a little more involved. It is not as easy as if G and L are not going to change with time. Had L been a fixed matrix, G another fixed matrix, solution would have been easier to do. So, this is one difficulty with respect to solving these equations. So, how does one eliminate this difficulty? One has to see why this difficulty arises. Why is it that L matrix and G matrix are going to change with respect to time? And if you look at the origin of the angle expression that appears in this, one can see that it arises because of the situation here. You have the alpha s axis which is fixed in space, because this pertains to the stator and the stator does not rotate, whereas alpha r axis is moving in space. It is moving in space because this pertains to the rotor and the rotor is rotating, and therefore whenever you have an excitation on the alpha r axis and something on the alpha s axis, the angle between the two is going to continuously change with respect to time as the rotor rotates, and therefore the mutual inductance between these two is bound to change. One can't avoid that at all, and therefore if you want to have a description that is independent of the rotor angle, that is feasible only in a system where all these are fixed with respect to each other. Suppose you had a hypothetical case. Let us say you are not having this alpha r axis, you do not have the beta r axis. Let us say you had a coil, another coil here and another coil here. This coil does not move, that coil does not move, these two also do not move. If there is not anything that is going to move, obviously all the inductances are fixed, there is no variation in the inductance, and therefore the flux linkage expressions would not involve the rotor angle. If the flux linkage expression does not involve the rotor angle, the derivatives and so on, all of them won't involve the rotor angle, and therefore this L and G etc., they are likely to be fixed. They won't vary with respect to angle and with respect to time, and therefore we would like to see if we can again do some kind of algebra, transform the set of equations that we have got in order to reflect a system like this, where these coils are fixed with respect to each other. So how does one do that? Again one has to start with the MMFs being equivalent, because any machine that we are any route that we are going to take must establish or must result in the machine behavior being unchanged. So if we have the alpha beta axis here, you have a coil here and you have a coil here, any MMF that is produced by alpha r should be produced by any other excitation system that we consider, only then the two are equivalent. So let us look at that situation and see what happens by doing this. So the alpha s coil is already fixed in space, so we need not do anything to that. It is only this coil and this coil that are moving. So in order to see how we can proceed, let us consider the MMF produced by alpha r and beta r. So let us consider some axis which is located at an angle phi with respect to the alpha s axis. We want to find out the MMF along an axis, along an angle phi, at an angle phi, due to the alpha r coil and beta r coil. There is some current that is already flowing here, there is some current that is already flowing here. Let us find the expression for MMF. So if we say that the MMF at this angle phi, if we call that as f phi, f at the angle phi, this can be written as the number of turns of this coil n alpha, we will put n alpha here, multiplied by I alpha into cos of, remember this angle is the rotor angle, that angle is the rotor angle, and if you want to find the MMF component at this angle, you need to multiply it by cos of phi minus theta r, that is the component of MMF produced due to the alpha r that is there, and then you need to find out what is the component of MMF produced due to this beta at this point. So that again is n beta, and we know that n alpha and n beta are the same, so let us have that in mind, then multiplied by I beta multiplied by, we can say, sine of phi minus theta r. So let us expand this expression, n alpha and n beta are the same, so let us denote that by simple n multiplied by I alpha into cos phi cos theta r plus I alpha sin phi sin theta r plus I beta into sin phi cos theta r minus I beta cos phi sin theta. So, this is the MMF that is generated by alpha r and beta r at a given angle phi. Now, we can regroup the terms, there are 4 terms here. So, we will rewrite it as n into I alpha cos theta r minus I beta sin theta r multiplied by cos phi plus I alpha sin theta r plus I beta cos theta r multiplied by sin phi. What we have done is taken the first term and this last term into one set, because both multiply cos phi, and then taken the second term and the third term as one set, because both are multiplied by sin phi. But however, now this expression looks like some term multiplied by cos phi plus some other term multiplied by sin phi. So, if I now denote this as some current, let me call that as I r alpha into cos phi plus I r beta multiplied by sin phi. This expression means that suppose I had a coil here, let me draw that by a different color. Suppose I had a coil here through which this current I r alpha is flowing, and I had a coil here through which a current I r beta is flowing. Then the MMF produced by this coil and this coil at a given angle phi is the same as what was produced by I alpha flowing here and I beta flowing on the beta axis. That is exactly what we have written. We started out with MMF produced by MMF at this angle phi produced by the alpha coil on the rotor and beta coil on the rotor, and we find that that MMF is the same as that which will be produced by a current I r alpha flowing on a coil having the same number of turns, but placed along the alpha s axis, and another coil placed along the beta s axis. Since the alpha s axis and beta s axis are fixed with respect to space, this coil is now fixed with respect to space. Similarly, this coil is also fixed with respect to space. Therefore, these coils, this one and this one, they are called as pseudo-stationary coils. Why pseudo-stationary? Because the actual MMF is not being produced by these two coils, but are being produced by the rotating coils. It is the rotor coils that are producing the MMF, and we find that we can imagine two more coils on the alpha and beta axis which are fixed in space, but having a fictitious flow of current through them which equivalently produces the same MMF. We give a notation as I r alpha to this. Why we call this as I r alpha? Let us understand that. Now, I r alpha is I alpha cos theta r minus I beta sin theta r. That means this flow of current, a fictitious current flowing into this fictitious stationary coil or the pseudo stationary coil, is a result of both the currents alpha, I alpha and I beta. The flow of current in the rotor is now mapped to a current flowing along the alpha axis of the stator and another current flowing along the beta axis of the stator. So, we will use this notation to denote that the rotor currents are mapped to the alpha axis. Similarly, you have the rotor currents mapped to the beta axis as I alpha sin theta r plus I beta cos theta r. So, the flow of currents in the rotor both alpha and beta are now mapped to the beta axis of the stator here. This is mapped to the alpha axis of the stator. This can be represented also in the following form using the matrix notation as I r alpha and I r beta is equal to cos theta r minus sin theta r sin theta r and cos theta r times I alpha I beta. So, if we do this, then we find that these currents are really flowing in stationary coils, albeit pseudo stationary coils, and these are fictitious currents. These are flow of currents in the two phase machine, which we have arrived at from the three phase machine. So, in this manner one can now try to transform the flow of currents in a rotating reference frame, that is alpha beta reference frame, into a pseudo stationary reference frame, which is alpha beta again, but these are fixed to the stator. This is only with respect to alpha and beta. How do we deal with the other term, which is V0 or I0? We do not do anything to that, we keep the I0 term as it is, and therefore this would be 0 0 1 and 0 0 here, and therefore this equation now defines a relationship between the alpha beta reference frame and the pseudo stationary reference frame. So, we now have a description as I r alpha beta 0 equal to another matrix, let us call that as D 2 2 multiplied by I alpha beta 0. Now, we would also like to have power invariancy here. So, if we use this idea, we can try to get a relation between V alpha beta 0 r and V alpha beta 0. I will leave you to look at this and see what could be the equation relating this and this pseudo stationary term. We will look at that in the next lecture and then see the implication of going from a rotating reference frame to a pseudo stationary reference frame. How does this affect the machine equations, and whether this will have any implication on the dependency of rotor angle. We will see that in the next lecture.